Okay, we were talking about the simple flow system, a tank with free outflow. Here's the diagram of this. So a quick review. Okay. Arkadaşlar diğer bilgisayardan da baktığım için görüyorum gecikmeyi. Biraz ona göre yavaşlıyorum yani. Kaçırdığınız bir şey var mı? Alright. So let's continue. So let's start constructing our model. Okay. So what we will do is we will start with Bernoulli's law. Okay. Bernoulli's law. Basically, it states how the tank level affects the velocity of the liquid out of the outflow pipe. Okay. So Bernoulli's law determines the relationship between the tank, between the outflow speed, outflow velocity. Oops. Arkadaşlar, tabletim kendini attı bir şekilde. Bir saniye. Hala toplantıda mıyım arkadaşlar? Buradan. Bir saniye.
Evet.
Ama screen sharing'im gitti. Bir saniye. Share screen. Şöyle yapacağız. Arkadaşlar sesim geliyor mu?
Geliyor hocam.
Fakat ekran görüntüm gelemedi. Bir saniye. Şöyle yapalım. Eskiden televizyonda yayın problemleri yaşandığında ekrana bir şey konurdu. Böyle vazo falan gibi bir şey koyup saplı maşrapa falan gibi böyle bir etnik bir malzeme konulup yayına ara verilirdi. Bizim de öyle bir şeye ihtiyacımız var galiba. Bir saniye. Hala uğraşıyorum. Tekrar ekran paylaşımı yapalım. Şeyden atıldık. Bir saniye. Bana ne oldu? Bir saniye. Bu arada sorularınız varsa sorabilirsiniz arkadaşlar. Bu teknik problemi çözerken.
Deneyleri nasıl olacaktı hocam onu? Oraya asistanımızı mı izleyecektik yoksa?
Deneyler şöyle olacak.
Olacak mı?
Deneyler şöyle olacak.
Kim konuşuyor?
Erdem.
Ha.
Kim konuşuyor?
Bir saniye, benim kendi sesim geliyor çünkü mikrofonumu kapatmayı unuttum. Kendi sesimi başka birisi zannettim. İlginç bir tecrübeydi. Evet. Şöyle deneyler laboratuvarda bir çeşit virtual presence ortamı ayarlamaya çalışıyoruz. Orada TeamViewer'la deney bilgisayarına bağlanacaksınız. Aynı zamanda grubunuz içerisinde de bir Zoom seansı yapacaksınız. Bu sayede bir taraftan deney düzeneğiyle etkileşirken mümkün olduğunca deney düzeneği zaten bilgisayarın üzerinden kontrol ediliyor olacak. Kendi aranızda deneyle etkileşebileceksiniz. Birden fazla kişi TeamViewer'la bilgisayarı kullanabiliyor. Orada kendi aranızda koordine olacaksınız. Aynı zamanda asistanlarla bir kanalınız açık olacak. Onlardan yardım istediğiniz zaman da onlar hem sizin Zoom toplantınıza katılabilecekler hem de deney setup'ı ile ilgili etkileşim ihtiyacınızı giderebilecekler. Bakalım nasıl olacak. Okay, so you guys have my screen. So we started with Bernoulli's law that determines the relationship between outflow velocity of the liquid. Let's call this V out of T. Okay, so that means there is here a velocity of the liquid, V out of T. Okay, so the liquid shoots out with a certain velocity, which is in meters per second. And our tank level, water level or liquid level, whatever, liquid level. Okay, so this is clearly a domain knowledge, right? So knowledge. So if you are trying to model such a system, obviously you need to go back and look it up how that behaves. Okay, so Bernoulli's law says the V out of T, the velocity of the liquid, will be the square root of 2 times the gravitational acceleration g and h of t. Okay, so g being gravitational acceleration. Okay, so if we check these units, right, V out of T is equal to meter per second, and we have square root of the unit of G is meter per second square is acceleration, and we also have meter for the height of the liquid. So you basically have square root of meter square over second square is equal to meter per second. Okay, so that verifies that this is a correct formulation. Okay, because the velocity unit matches the output of the calculation of the unit. Okay, we are not, maybe mechanical engineers, for example, are kind of much more serious about these units issue, but I think it's also important for us that I don't know, maybe in some of your other courses that I'm not teaching, you are kind of more rigorous with the units, but at least in the courses that I am teaching is only raised in the process control courses to this extent. Okay, now let's continue. The second relationship is that we need to write down the volumetric outflow rate based on this velocity formula. Okay, so volumetric, by the way, outflow rate will be Q out of T. Remember, this is a free outflow, so it's going to be really determined by what's happening with the level of the tank, the output velocity, the output velocity because of the Bernoulli's law. So Q out of T is equal to, again, I'm going to make the calculation using the units, the area of the outflow pipe in meters square times the velocity V out of T in meter per second. Okay, so that's going to be A times V0 of T, and the unit will be meter cube per second, which is consistent with a volumetric unit. Okay, we had already defined our volumetric outflow rate as meter cube per second, so that also verifies that this formulation is correct in terms of units. Okay, the third step is what is the volume of the liquid in the tank. Volume of the liquid in the tank will be equal to, let's call this T of T, is obviously related with the area of the tank, A, times the height of the tank. Okay? Again, remember in terms of the units, right? Area is basically meter square times the height, which is meters. So that makes a meter cube, which is consistent with the volume, units of the volume. Okay? So that's another check here. Finally, in order to construct the differential equation, we note that the change of the volume of liquid in the tank is determined by the difference between the inflow, volumetric inflow is what we mean, inflow of liquid, and the outflow. So if we know the inflow and the outflow, we can determine what's going to be the change in the volume of the liquid in the tank. Okay, this is known as the mass balance equation. And clearly it is another example. Okay, so it's another example of a conservation law. Okay, basically example of, or not an example, but an instance rather, an instance of fundamental conservation laws. I mean, all of this comes to the conservation of matter, right? You cannot have matter disappearing, and you cannot have matter appearing from nowhere. Matter needs to be conserved. So if there is a difference between the inflow and outflow, you need to have an accumulation of matter inside the vessel. Okay? But we also make an assumption here is about the density of the liquid, right? Because the material, the amount of material and its volume is related by the density. So we assume that the liquid density is constant. Liquid density is constant. Otherwise, we would have, for the same volume of liquid, we would have different amounts of material. Okay? So what is the equation? The equation is the change in the volume, which is also equal to A times the change in the height of the liquid, okay, because of our formulation beforehand, is equal to Q in of T, which is the inflow, minus Q out of T, which is the outflow. Let's put in everything that we have. So we have A times dH of T over dt is equal to Q in of T. By the way, what can be considered as the input and the output of this system here? What do you think? What is the input to this system?
Q in input, H dash out.
Very good, right? Q in of T is the input, and a possible output is basically what we are really interested in our problem. So we can have H of T as the output of this system. Okay? So that's a small note here. So let's continue. Q in minus A times V out of T. And if we continue putting in, that is equal to, so let me put it here because I'm kind of squeezed there, is equal to, again, q in of t is already an input variable, minus a times square root of 2g h of t. And if we kind of simplify it a bit, it's going to be a times square root of 2g, this is a constant, right, times square root of h of t. Okay, so that's our differential equation. So it's a first order differential equation with constant coefficients. Is it linear or nonlinear?
It is nonlinear.
It's a nonlinear equation, right? I mean, you can also obviously take this term to the left-hand side if you want and leave only the input on the other side, okay? All right, so that's kind of, you can consider this as a state space equation as well, because it is a first order differential equation. So h of t can be considered as the system state. And usually state space formulation, because it's in the time domain, it allows multiple inputs, multiple outputs. It also allows nonlinear state space equations. So with state space formulation, you can also work with nonlinear systems. And we know that we cannot transform this into Laplace domain. We cannot obtain a transfer function because of the nonlinearity. And what is the source of the nonlinearity here? What actually injected the nonlinearity in our system?
Variable is not in the simplest form.
Reality maybe.
Well, I didn't understand what you meant by that. My question was, in our model, what was the source of the nonlinearity?
E0 bence. Kök falan getiriyor.
Yes, but you can just say, it's the Bernoulli's law, right? It's a nonlinear relationship between the height and the velocity. So that part really is the one injecting the nonlinearity in our system, right? So nonlinearity arises because of the Bernoulli's law in the system. All the rest of the relationships are linear relations. Any questions so far?
Volume change'de t, niye t olarak variable'ı kullandık onu soracağım.
Volume change'de neden T olarak kullandık? Öyle bir şey attık yani, tank, T for tank, whatever. Okay? It's not a magical thing. I mean, maybe not to confuse with velocity. We already have a V variable. So, but there is no special reason for that. Okay? You can use any variable that kind of reminds you of the physical variable underneath. Any other questions?
Hocam
Yes.
TS neden dedik hocam? TT aşağıda.
TS dememiz tamamen bir
Biraz aşağı
saçmalıktan ibaretti. TS tabii ki demememiz lazım. Yani sonuçta burada T olması lazım.
Tamam hocam.
Tamam. Teşekkür ederim düzeltme için. Başka soru var mı?
Hocam, ben
Benim
de
düzeltmem biraz geç geliyor oraya ama düzelttim yani şu anda.
şu out hocam kök 2GH olarak yazdık ya.
Evet.
Bu sıvının hani akıcılığı tarzı bir özelliğe bağlı değil mi? Bir şekilde?
Sonuçta eğer sıvının density'si constant olduğu takdirde, yani sonuçta hani sıvıların akışıyla ilgili bütün detayları bildiğimi iddia edemem. Ama sonuçta Bernoulli yasası sıvının yüksekliği ile akış hızı arasında bir ilişki veriyor. Nonlinear bir ilişki. Eğer density sabitse density'den bağımsız olarak böyle bir ilişki olduğu söyleniyor. Ama
Ben düşündüm de.
düşünüyorum, sonuçta sıvı koyulaştıkça, değil mi? akış hızının yavaşlaması gerekir mi? Gerekir gibi geliyor. Dolayısıyla acaba bu formülün, ona bir bakar mısınız? Belki de bu şeyin içerisinde bir density terimi olabilir de belki örnek bunu suyla bir olarak almış olabilir. Makul mü söylediğim?
Tamamdır hocam.
Yani
Bakıyorum
sorunuz
ben.
bence
Hocam bu
mantıklı bir soru.
Muhtemelen hocam density'den ziyade viskoziteye bağlı olabilir o.
Evet. Evet ya, orada bir ekstra terim olabilir. O zaman şuraya şöyle bir şey koyalım. Check any dependence on a viscosity term question mark. Okay. Which means we have just ignored that for this example. Okay, but if there is such an extra detail, this is where you would put it in, right? The Bernoulli's law part is where you will also consider that term. Probably you will assume that that's another constant in the equation. Okay, so that's not going to change the basic kind of nature of this relationship, where you have a square root relationship with the height of the liquid. Okay. All right, so let's have a small break here. Let me let's open up our exercise in Metu class. And let's complete that. Okay. Let me close my sharing. And please go to the course website. Under this week, there will be a Omega 4.2 session exercise. Oh, I'm already kicked out. Hold on. Let me also